Hi everybody, it's Mr. Zarzak, and in this screencast I'm going to review how to do two-dimensional vector problems where objects move with constant velocity. If you'd like to work along with me, I'll be working questions 1, 2, and 3 from the Vector Projectile Test Review handout that is available on the course website. Okay, so to do these first group of problems, there's a couple of numbers that we're asked to decide on for ourselves here. It says a boat sailing with a speed of, I think I'm going to have my boat going at 6 meters per second, and we'll have our boat trying to sail west through a stream that flows, how about south, at a speed of, let's go 4 meters per second. All right, so question 1 says, what's the resulting velocity of the boat? To help me solve this, I'm going to draw a picture. You're always going to have a picture, and in a lot of cases it's going to be required. So let's see here. I got a little space up here on the right. So I'm going to start by making a little compass rose, and I'm going to define this direction as north. So then going clockwise around my compass rose, never eat soggy waffles for north, east, south, and west. All right, we've got a boat going across the river headed west, so I'm just going to make a little sketch over here, and I'm going to draw myself. There's my river. All right, and then let's see, for my boat is headed west, so this arrow here represents the velocity of the boat just by itself, and then the river is flowing south at 4 meters per second, so I'm going to draw the velocity vector for the boat going to the south, and notice how I've got these two vectors lined up tip to tail because I'm going to use that to get the resulting velocity. All right, so I'm just going to label these. The velocity to the west, I'm going to call that Vx. All right, and the velocity to the south, I'm going to call that Vy. Okay, so we're kind of sticking with like XY axis like we would have in math class. All right, and then to draw the resulting velocity vector, those go from start to finish. So this right here, that arrow is going to represent the resulting velocity of the boat, and we're going to name that V. Now, there's one more thing I also want to label on my diagram, and that comes from the fact that this question says, what's the resulting velocity of the boat? All right, now velocity is a measurement of speed and direction. This V here, I'm going to solve for the hypotenuse of this triangle. That's going to give me the speed part. In order to get the direction, okay, well, the boat travels at some direction, somewhere south and west, but I'm not exactly sure how far. All right, that's something I have to calculate. So the way I calculate it is I find theta. So I'm going to go through and I'm going to recap, all right, my horizontal velocity Vx. That's the 6 meters per second. All right, and the boat goes west, which is why that's horizontal. All right, my Vy, that's 4 meters per second, and that's to the south. All right, the things that I need to solve for are the speed of the boat, V, and the direction of the boat, theta. These two things together, that's what's going to give me my total velocity, those two numbers. Okay, so now we're ready to solve. So let's start with the magnitude of the velocity, or the speed. All right, to get that, we're going to apply Pythagorean theorem to find the hypotenuse of this Vx, Vy, and V triangle. So V is equal to the square root of Vx squared plus Vy squared. And so if we sub in our numbers, all right, our Vx is that 6 meters per second squared, and then I add that to the Vy, which is 4 meters per second squared. And if we calculate that, we'll find 7.211 meters per second. That's the speed part. So I'm going to go ahead, I think I'm just going to label that just so I don't forget what it is that I'm calculating. All right, so that's the speed. And now we go on to the direction. To get the direction, I'm going to look back up here at my diagram and say, okay, well, we've got this angle here. All right, so I'm going to use Vy and Vx. If I was thinking of this as a SOHCAHTOA triangle, this part of the triangle, we call that the opposite. This would be the adjacent leg, and then, of course, this is the hypotenuse. So to do this, I'm going to use the inverse tangent function. Tangent is opposite over adjacent. That's the TOA in SOHCAHTOA. So direction equals the inverse tan of, in this case, I've got Vy divided by Vx. Theta is equal to the inverse tan of my Vy, which is, that's the river, that's the 4 meters per second, divided by Vx, that's the boat, that's 6 meters per second. And then again, we're going to throw that into our calculator. Reminder once again, when you do this in your calculator, make sure your calculator is set to degree mode. And if you do it right, you'll get 33.690 degrees. And that right there, that is the direction part of the velocity vector. Direction. So these two things together, speed and direction, make up the velocity of the boat, which is what we're asked to solve for in question number 1. Notice that I've also saved 3 digits past the decimal point so that if I have to solve something like this on WebAssign, I won't get any rounding errors. Moving on to question 2, okay, we're asked to decide if the stream is blank meters wide, so I'm going to make my stream 77 meters wide. How long does it take the boat to cross the stream? So I've just gone ahead and pasted in the information that I had from part 1 of the problem along with my diagram because I'm still going to use it, all right? So it says here the stream is 77 meters wide. So from one bank of the stream to the other, from here to here, okay, that's that 77 meters. All right, we call that, that's a distance straight across. It's in that east-west direction, so we call that dx. All right, now the key with these kind of problems is that you got to match up the directions. And what I mean by that is since we have information about the horizontal distance of our river, all right, if we're going to solve for anything, and in this case we're solving for time because it says, well, how long, so how much time does it take to cross the stream? All right, in order to do it and get it right, all right, we have to use the horizontal velocity, this 6 meters per second west. We're not going to use the diagonal here because we don't have a diagonal distance, we've got a horizontal distance. All right, and that's probably the trickiest part of these, but once we realize that or once we see that, okay, well then this becomes a pretty straightforward calculation. All right, displacement equation just says D equals VIT plus 1/2 AT squared. Now, we're looking in the horizontal direction, so any quantity that's a vector here, we're going to put a little x with it. So this is dx, this is VIX plus 1/2 AX times t squared. But the good news is that, well, these problems are all constant velocity. There's no information about any acceleration or speeding up or slowing down, and these are not projectile problems, so nothing's moving through the air. So the nice part is that there's no acceleration involved at all, in which case our equation becomes dx is equal to Vx times t. The initial velocity is the final velocity, is the average velocity. It's just the horizontal velocity, which is pretty nice for us. All right, the dx is the given 77 meters that we decided up at the top of the problem. All right, the horizontal velocity, okay, well, we picked that 2. That's the 6 meters per second. So 6 meters per second times the time to get across the river. So all we have left to do is divide out 6 meters per second. All right, to both sides. All right, and so the time is just going to be that 77 divided by 6. All right, and I have that calculated out. That's 12.833 seconds. All right, the boat spends just under 13 seconds crossing this river. And now question 3 asks us to find how far the boat is swept downstream. All right, so the key to doing this really comes from the word downstream. All right, so the idea here is that the boat sets sails, let's say here on the riverbank, and is attempting to sail straight across the river. So what's the boat's trying to do is trying to land approximately here. The problem is that the river is flowing south. All right, and so the reality is that the boat moves along this diagonal path and is going to wind up landing somewhere down here. And so the boat gets swept downstream like this. All right, so we call that the distance y, the dy for downstream. So just like with solving for the time using dx, we needed to use vx, because we've now got a vertical distance that we want. We're going to have to use this vy. We're going to need to use this 4 meters per second. And so this is kind of the general rule of thumb with working these vector problems, is you always have to match the directions. All right, and so again, this is just an application of the displacement equation. D equals VIT plus 1/2 AT squared. All right, where I'm looking at things in this y direction. So anything that's a vector, again, I'm going to go through and I'm going to label it with a y. So we've got dy, we've got vy, and we've got ay. But again, this is a constant velocity problem. There's no information in the problem about things speeding up or slowing down, and this is not a projectile problem. Nothing's moving through the air, so there's no gravity involved, so no acceleration. And we like that because that makes the problem easy to solve mathematically. Dy is equal to Vy t, and notice I'm dropping that initial part of the velocity because the initial velocity, the final velocity, the average velocity, they're all the same if there's no acceleration to our motion. All right, so this really turns into a one-step plug and chug. All right, looking back up, my vertical velocity, dy, is 4 meters per second. The time to cross the river is 12.833 seconds. Again, the time that the boat spends moving horizontally across the river is also the time that the boat is getting pushed down the river. So, just going to throw in my numbers here. Dy is equal to 4 meters per second times my time of 12.833 seconds. Multiply those two numbers together, and you'll get 51.333 meters. That's the distance the boat winds up landing downstream. Okay, and then one last little thing I wanted to mention. All right, is if I scroll back up to my diagram, all right, we'd calculated the direction to be 33.690 degrees, and we've got our angle labeled on our diagram. So we know what angle we're talking about. Just to kind of put some words to go with that, all right, because this stuff can be pretty confusing. All right, the boat was attempting to sail to the west, all right, but unfortunately the current pushed it to the south. So this angle here is a measurement that goes like that. If I go over to my compass rose, okay, you can kind of see it here. The boat was attempting to sail to the west and it got pushed to the south. So if I was going to put that resultant velocity right on my compass rose, it would be like that. In which case, the way that I would measure the angle is going south from the direction west. See how that angle starts at west and goes towards the south? So if I just add that to the 33.690 degrees, okay, that direction would be 33.69 degrees south of west. And there we go. We've got a complete description of this boat sailing across this stream, getting swept downstream by this current. And that about wraps up this screencast. All right, so now you go back, pick some numbers for yourself, and try one of these in practice. Thank you for watching, and good luck.